Welcome back, everybody. We're now talking about things falling down. So we're looking at sleds and we're looking at things on ramps and skateboard ramps and all kinds of things because we're going to break down the components into different components. We're going to use a little bit of our baby trig. Actually, it's even less than our baby trig to do this. So first of all, you know that weight is going to pull something towards the center of the earth. So if you have something on a slanted incline like this, weight is always going to go straight down. Depending on, doesn't matter how steep that the incline is, weight is always down. But since you have a surface, you are going to have, remember, a normal force or support forces coming straight out at 90-degree angles to the surface. And you're going to have part of this weight that is counteracting that support force. That's the reason why that it doesn't fling up into the sky or fall down into it. So part of this W is actually broken apart into straight down, and part of this W is into straight up. So the first one here is showing you that part of it's going straight out, and this is why that you can imagine that this box would actually slide down the incline. And the steeper, of course, the steeper it is, the more that this is going to be longer and the more likely it is to slide down the incline. Okay, the flatter it is, the less steep, the less it'll be inclined to slide. Okay, so part of this W is this. The other part of the W is the one that is counteracting the normal force, and it's going to be exactly equal and opposite to the normal force. Whatever this is exactly the same force that's being pushed up on the box by the incline. Okay, so this is a perpendicular force and this is a forward force, both of these made up. The W is actually the resultant of this and this. We talked about that yesterday. Okay, so here's a steeper incline. You've got the same situation. So draw the components. Well, remember a parallelogram rule. The resultant is going to be into the corner of the parallelogram. That means that this part is going to extend. This is the center of gravity, is going to extend down as far as that. And then the support force is going to be equal and opposite to it. So coming out from the incline into the box would be the support force equal and opposite to this. Then you're going to have a force acting down the incline, and it also is going to only go to this part because we want a parallelogram in order to find out if this is the vector of force, then this much of it is going to be here and this much of it is going to be here. Now it's better if we can actually find out the numbers of that, and you can do the numbers by simply making a right triangle. This is the hypotenuse, this is A, and this is B. So A squared plus B squared equals C squared. And so there's some math that you can do to find out what the resultant, it breaks down into the components of the resultant. Okay, so it said for a steeper incline, the component parallel to the incline, so this one down here, is it greater, is it same, or is it less? Which one has more of a tendency to go forward if you put it on it? One on a steep or one on a shallow incline? It would be greater. Okay, greater. It would be the steeper it is, the taller this component is, the more force is actually pushing this box down the incline. For a steeper incline, the component perpendicular to the incline increases or stays the same. Okay, the component perpendicular to the incline. Perpendicular is the one coming down. So as this one is getting bigger, what happens to this one? Okay, here is the original, and we saw that the original, it's not as steep, and you see that this one's actually reducing. This one was very short, and it gets longer. This one was very long, and it gets shorter. So the steeper the incline, the more its tendency is to go forward, and less it is to sit. Remember, this straightward down is forcing it into the inclined surface. As this is less and less and less, this takes over, and eventually it slides down. Okay, so this would be decrease. As the steeper it is, this perpendicular force decreases. Draw components of each weight vector parallel and perpendicular to the surface for the block shown. Okay, so we have a nice shallow one here, and we want perpendicular lines. Okay, so we want a perpendicular line here, and then a perpendicular line here. Okay, so that means that the force is going to act this. It's not likely to go forward. It's probably just going to sit there, and then this force is really long, and it's pushing itself into the incline. It'll sit there. This is steeper. Okay, so I want a perpendicular line. So I need something that's going to, remember, this is going straight out. Okay, and this is going to be at the opposite corner of this parallelogram, and so it's going to go here. Okay, I think that's right. And then that's a parallelogram there. That means this component is going to be here. So this is farther down. This is more force, so it's more likely to fall than this one, and less likely to stay put because this force is less. Okay, this is very steep. Okay, so what's going to happen here? Remember, this is going straight down at 90 degrees to the surface, parallel to the surface, and we want this to be perpendicular. This is coming straight into the board, so this is perpendicular. So I've got a nice box there, and so you have really a far vector here, really far, and not very far acting here. Okay, and then this one ridiculously steep. Okay, let me turn this a little bit so I can draw it. This is coming straight out, and this is coming straight down. Okay, and I want its weight. Now its weight's going to be the same because the box is the same, so the weight is going to be the same. So the weight, something like that, whatever the same is here, I just make it the same. That means this has to go very far down, almost to the floor, and then this one is very short. So this is a short runty one, and this is a huge force out this way, and then this is weight. So this is weight, and here's the parallel force, and here's the perpendicular force. A block slides down a friction-free ramp. I'd like to have a friction-free ramp. Construct components of the weight vector. One parallel to the surface A, B, and C, and the others perpendicular at surface locations. All right, so we're going to do exactly what we did here. We're going to do it here. I want one to go straight down, so I'm going to go from the center of gravity straight out. Okay, then I'm going to have one go straight in, and then this has to be, I'm sorry, I can't draw, it's all sideways. So that's ridiculously steep. There's no way it could stick because even its weight is not in the base. It's not under itself, so it's going to definitely fall. So this is going to be forward here, and this is downward here, really small. Towards the middle, it's more balanced, more evenly balanced. One is going to go straight out. Better move it a little more. I don't know where that's going to be. And then this is going to go straight down, and I'm looking for a parallelogram. So a parallelogram is going to be kind of a box in this case. So we're going to have, so there's a forward parallel, and here's a perpendicular force. Once it gets to the bottom, is it going to continue? See, now the weight is actually under the base, so it's not likely to tip over. This would be likely to topple if it didn't slide. So I'm going to have a 90-degree vector here, and then a 90-degree vector here. So what we got? Okay, it looks like probably have something like, oh, I'm wrong. I shouldn't have just put an arrow. I need to make a parallel. It only goes this far, so it's not going to want to go very far at all. It's basically wanting to sit. Okay, so this is all garbage. All right, so what's it say? At which location is the component parallel to the ramp the greatest? Okay, well, parallel to the ramp is here, and it's way bigger than the other two. So definitely A. Okay, at which location is the acceleration of the block along the ramp the greatest? Okay, acceleration. Which one's moving the fastest? Well, this is probably moving the slowest, right? Because it's not even wanting to move forward very much, and most of its weight's directly under it. It's just going to sit there. This one is going to move some. This is probably the acceleration with the greatest. How would I decide how that is? The force that's making it accelerate is the largest. So the force pushing it is going to be related to the acceleration. So the bigger the force, the more the accelerated. So this would also be A. At which location is the acceleration of the block least? Obviously C. True or false, the speed of on the block on this ramp is greatest where acceleration is the least. Okay, the speed is the greatest where acceleration is the least. I don't know, you'd have to really think about this. This is starting to slide, okay? So the energy here, we're going to see this in a later chapter, but the energy here is stored in its height. And as it's falling, it's going to turn from stored positional energy into stored movement energy. And so actually, this is going to move pretty slow, faster, fastest, okay? Now, it wants to actually slow down also because there's more force out, less force in. But if I just put this box here, just put the block down on the end, it probably wouldn't move. But if I sent it here and let it slide, it would probably slide right off the end. So this would probably be moving faster than that. So what does it say? The speed of the block on this ramp is greatest where acceleration is the least. Here's the acceleration the least. And yeah, it is true because all of that energy is pushing it out, and that's why it's going to go the fastest there. Okay, flip this over. Oh no, two sides? This is resultants, vector resultants. Okay, so on the previous page, we considered only the weight factor, that's W. Remember, that's mg, weight equals mass times gravity. Only the weight vector W for the block on a friction-free incline. Here we also consider the normal force. If you remember the normal force, they've got it coming out. I always think of it as coming in. So if I have a normal force coming down this way, I'm also going to have a normal force pushing in. Problem is that they can't be in the same location because it would confuse you. Like if I put it here and then also shoved it up into it, you're not sure. It would just have two arrows and that wouldn't make any sense. So what they did is they showed you that the force, which is actually exerted from the incline, is pushing this block up. Otherwise it would fall into the incline. So they're showing a force here, and then you can have another parallelogram. You have weight coming down, normal force coming up, and then you're going to end up with 3. You're going to have a perpendicular component. So that would be going down, not parallel, not perpendicular, parallel component coming down. And it's going to be a perpendicular line between the end of the normal force and the end of the weight. And so these two things are actually going to cancel. For instance, if I had normal force coming down, okay, like this, that's a normal force coming down. You could see that this is what we did on the last page. We made weight be a normal force, which is equal to this. This is the weight down, the weight, the perpendicular component of this weight, and it's equal and opposite to the normal force because they cancel each other. And then whatever's left over is going to be this forward force. So we construct a parallelogram whose sides are W and N. So here's W straight down, N out. The resultant of the diagonal, the bold vector, this is the net force on the block. This here is what's making the block move. If you have a net force that's not canceled, it is what is accelerating the object. Whenever you have a net force, it accelerates. Okay? So let's look at some of these examples here. Note the net forces, which are bold, for the blocks below. Okay? So number A, for a steeper incline, the normal force does what? Okay? So the steeper it is, what happens to the normal force? This is the normal force. Here's the normal force on a shallow incline. Here's the normal force on a very steep incline. So what's happening to it? It's decreasing, okay? Because the component wanting to go in is also decreasing and they're equal to each other. For a steeper incline, the net force does what? Okay, the steeper it is, so here was the net force at the beginning, here's the net force, it's growing, it's growing, it's growing. This one's huge. The net force is making it fall. So if you put something on a steep incline, you're promised to let it go forward. If you put it on shallow, it may not move at all. Okay, so this would be what it's going to increase. And C, how does the net force compare to the parallel component of W determined in the previous page? Right? Well, remember the parallel component? That is the net force, because the weight, the part of the weight is broken down in two parts. A perpendicular force, which is counterbalanced by the normal force, and then the rest is the net force, which is not counterbalanced, and it's causing motion. So this is going to be the same. All right. Number 5. The block slides down a curved ramp as on the previous page. In each location, the net force resultant in N is parallel to the ramp surface. Draw N for locations A, B, and C. Okay, so, all right, so we've got, remember, this is going to be broken into two parts. The first is going to go straight down. This is its weight, and so you're going to have a component going straight out. That's the net force. Okay, and then this is coming straight out. So this is the normal force here, and I want something to be similar to that. Okay, you can see that these two are parallel and these two are parallel. So you have a nice long, this is the net force here, the little N. Okay, this is the normal force coming out, and it's equal to the perpendicular component of weight. Okay, for B, okay, here's the normal, it's coming out nice, equal to this, whatever this is, that's going to be. And so I need a component that's going to be essentially a parallel line. Okay, and so this is coming straight out of here down to this point. Okay, so this is net force here. And then the last one is really simple because this is huge. Okay, it goes all the way down to here. This one is very shallow, and then this one is it's going to be equal to this, whatever that is. And then we want a perpendicular line, so it's going like, this is perpendicular to this. This is perpendicular to this. I'm doing it badly. No, this is like that. That is perpendicular. So this cancels with this, and this is the resultant force. Ooh, that was bad. Okay, which location is the net force the greatest? Well, this is the net force. It's longer, so it's A. What about which location is acceleration greatest? The bigger the force, the more acceleration. This is also A. As the speed of the block increases, acceleration does what? Increases is constant, decreases. Okay, so as it speeds up more, as the velocity speeds up more, it doesn't continue to get faster. The velocity is increasing, and the acceleration is actually decreases. Okay. I'm sure some of you were iffy on that one. And the last one, on inclined flat planes. So this is a curved plane. On inclined flat plane, acceleration down the incline is constant or it varies. Remember, at the Earth, is gravity constant? Yes. So acceleration down a certain pitch, whatever that steepness is going to be the same. It may not be 9, it may be 1 or 2 or something, but it'll always be the same all the way down, so it's constant. On curved inclines, acceleration does what? It's higher here and is less here. That curve is actually going to make the acceleration faster down to slow, so it's varied. Curved tracks vary. Okay, nice and long. Thank you.